Hello, everyone. If you've tuned in for Woods Hole Oceanographic Institution's Ocean Encounters presentation about radiation, you're in the right place. Coming up, we'll hear from Texas A&M University nuclear engineer Shaheen Dewji, Princeton University nuclear anthropologist Rio Morimoto, and WHOI marine radiochemist Ken Buesseler. All that and more in just a few minutes. Hi, everyone. In just about a minute here, we'll get started with Woods Hole Oceanographic Institution's Ocean Encounters presentation, Radiation in Our Ocean, Our Planet, and Our Lives. We've still got a lot of people joining us, so thank you for your patience. Hi, everyone. We've still got some people joining us, so we're going to hang tight for just another minute here. But welcome to all of you to the Ocean Encounters virtual series from Woods Hole Oceanographic. You're joining us for radiation in our ocean, our planet, and our lives. And we'll get started in just a minute.
The ocean covers 70% of the globe. It gives us oxygen and food and millions of jobs. It brings joy and shapes our climate and weather. The ocean is life, and it belongs to everyone. Woods Hole Oceanographic Institution is the world's independent leader in ocean discovery, exploration, and education, working to understand and sustain one of humanity's most precious common resources. Join us today for our ocean, our planet, and our future.
Welcome to the Ocean Encounters virtual series from Woods Hole Oceanographic Institution, or WHOI, as we like to call it for short. Tonight's presentation is Radiation in Our Ocean, Our Planet, and Our Lives. WHOI's Ocean Encounters online events are made possible in part by the Avatar Alliance Foundation and Dalio Philanthropies. Thank you. My name is Véronique LaCapra. I'll be your host for tonight's event. Before we hear from our presenters, I'd like to take just a minute and share some tips on how you can optimize your Zoom experience with us. Later on this evening, our speakers will be taking questions from all of you. If you'd like to participate in that live Q&A, please use the Q&A button on your Zoom screen and type your question in the window that appears. You might be more used to the chat function in Zoom, but for tonight, please use the Q&A function instead. We often get hundreds of questions, so I apologize in advance if we don't get to yours while we're live. You can ask questions anytime, starting now. I also want to let you know that we are recording this event. That recording will be made available on the whoi.edu website. We had over 1,000 people pre-register for this event, so you're in very good company tonight. Thank you and welcome to all of you. All right, let's get started. Earlier this month, we marked the 10th anniversary of the earthquake, tsunami, and meltdowns in Japan. On March 11th, 2011, a magnitude 9.0 earthquake and 50-foot tsunami struck Japan, knocking out power at the Fukushima Dai-ichi nuclear power plant. The accident caused meltdowns, explosions, and widespread radioactive releases to the atmosphere, the land, and as we'll hear shortly, to the ocean. But human activities aren't the only source of radiation in our environment. There are plenty of natural sources too. Tonight, we'll take a close look at radiation all around us, its sources, its human applications, and their impacts on us and our environment. We'll also delve into some of the beneficial uses of radioactivity and the way we perceive or misperceive the threats that radiation poses. Before I introduce our panelists, I'd like us all to share a moment of silence to remember the more than 18,000 people lost as a result of the earthquake, tsunami, and nuclear meltdowns in Japan. Thank you. We have three panelists with us tonight to help us understand the complicated and controversial topic of radiation. They are Texas A&M University nuclear engineer Shaheen Dewji, Princeton University nuclear anthropologist Rio Morimoto, and WHOI marine radiochemist Ken Buesseler. First, thank you to all three of you for joining us this evening to talk about radiation in our ocean, our planet, and our lives. Let's start with Shaheen. Dr. Shaheen Dewji is a nuclear engineer with a specialization in health physics at Texas A&M and a faculty fellow of the Center for Nuclear Security Science and Policy. Her research focuses on radiation protection, measure the body's exposure and respiration, and the use of radiation in medicine. She also works on nuclear safety and security, managing risks associated with radioactive materials. Shaheen, thank you for joining us.
Thank you very much, and good evening to everyone. I'd like to thank the Woods Hole Oceanographic Institution for this excellent opportunity to speak today with you. As mentioned, my name is Shaheen Dewji, and I'm an assistant professor in the Department of Nuclear Engineering at Texas A&M University. Just before we start, I wanted to share my foray into nuclear, and it was honestly quite an unexpected one. I was initially a pre-med student, but I shifted my early education to my passion area of physics. One of my early internships was dedicated towards using nuclear technology, what we call neutron activation analysis, in fact, to look for landmines in Afghanistan. So this was one example of how I was exposed to a beneficial application of nuclear technology. I've since made a career out of developing technologies for nuclear material security and for the regulation of radiation safety before moving into a university arena where I've had the opportunity to develop innovative solutions to the energy, security, and medical challenges and applications of nuclear technology, while having the opportunity to support our next generation towards tackling these challenges, such as with cancer treatment and climate change. So to kick off our discussion, I'd like to start with the foundational discussion of radiation in our lives. One of the themes of our key panel today, right? We're here to discuss radiation in our ocean, our planet, and in our lives. I'd like to give you the tools, what you need to learn how to identify where radiation is present in our daily lives, and how to get a good gauge for how to evaluate levels of radiation dose amidst all the different perceptions and cross-cutting messages regarding radiation. So as you can see here, perhaps one of the most powerful factors influencing our perception of radiation stems from two major sources. The first is a very powerful legacy of nuclear weapons from the Manhattan Project, resulting in the 1945 bombings of Hiroshima and Nagasaki, which has certainly affected Japanese cultural perceptions and international perceptions, as well as the impacts of nuclear technology in a weapons environment. The anti-nuclear movement was born out of these World War II bombings, and we've since learned a lot about the impact and the effects of nuclear weapons, as well as the effects of radiation on human health. The result nowadays has been sort of within this public perception is that of, for example, here, one of megalomaniacs or evil scientists, as you can see here with Dr. Strangelove, or a more contemporary and realistic trigger of nuclear terrorism. Though I'd have to impress upon you that the idea of manufacturing plutonium, right? So building a reactor, baking it just under the right conditions, separating it out from spent fuel, which is still highly radioactive, smuggling it, so bypassing all domestic and international technologies, intelligence, and law enforcement networks, and effectively being able to detonate a weapon is a Herculean task. And another perception of nuclear is one of incompetence, as you can see here on our right from one of our favorite evening cartoons. So here on the right, we can see a kitty kangaroo type of cover of nuclear security procedures. And as well, we can see an example of how nuclear material is shown as unsafe handling. So just to caveat, in fact, our nuclear industry is one of the most diligently regulated industries with highly trained experts who are subject to internal inspections within the nuclear industry amongst themselves and subject to domestic inspections by the US Nuclear Regulatory Commission, while requiring adherence to federal policies such as from the Department of Energy, Nuclear Regulatory Commission, and the Environmental Protection Agency. Furthermore, new reactor technologies only increase passive safety inherent to their design. So there's no big red shiny button that you can press to make a reactor melt down to the core, like China Syndrome, another movie that makes some interesting reference to nuclear that is not entirely accurate. So in fact, the nuclear community, and certainly in the US and Japan, as we're discussing today, has one of the strongest safety cultures. So that would be a key takeaway that I would like for you to have today. Next slide, please. So let's discuss a little bit about radiation we encounter in our daily lives outside of some questionable perceptions on television. So here we have a pie graph that breaks down the average exposure to a US person per year. So we call this an annual dose. Right, so the whole pie, if we were to equate this in terms of dose, is 6.2 millisieverts. So a millisievert is 1,000th of a sievert, and that is a scale of radiation dose. In the US, we use traditional units, right? So if you see millisievert or millirem, 1 millisievert is equal to 100 millirem. So here we see 6.2 millisieverts, and I've done my best to ensure that we have the international system of units and the traditional system of units just off by a factor of 100. So 620 millirem. So right now, I want you to pick your camp. Are you going to be in a millisievert camp or in a millirem camp? And just follow that set of units through today. All right, so in our pie, we can see here in green what's called background radiation. This is almost half our pie. It's about 3 millisieverts. So radiation is around us all the time. It's part of our everyday environment, just as much as light and heat is from the sun's rays. The Earth has always been radioactive, so there's natural radioactivity in the environment, and that's about the same as it was 10,000 years ago in the Neolithic age. If you live in Pennsylvania, for example, there are rich deposits of radioactive ore in the earth. So if you buy a house with a basement there, you might have undergone a radon test. The water we drink, the food we eat. So for example, bananas have naturally radioactive potassium. The air we breathe, these all contain radioactive elements that contribute to the background, right? So there are many different kinds of radiation that can be beneficial and harmful under some circumstances, right? Even if natural. For example, none of us would be alive without radiant energy from the sun, but excessive exposure can cause skin cancer. Keep this in mind, though. A lower long-term exposure is what we call chronic. So I want you to remember this idea of chronic. It's long-term. So when we think about long-term, if we're thinking about the sun's rays as an analog, right, this is maybe what would happen is you would get a tan. You have low levels of radiation that you're exposed to over a long period of time, and the body has the opportunity to repair itself. The opposite to that is acute, which is for example, if you tan too frequently, or if you go to a tanning bed. Acute is like if we would get a sunburn, so a high level of radiation in a very short period of time. So this is acute, and chronic can be considered regardless of the type of radiation, just like a suntan or a sunburn. In blue on the other side, we can see non-natural sources that are attributed. Almost a little more than half the pie is due to medical procedures, so scans. So this is an average US person. You might look at this and say, well, I didn't necessarily have a medical scan last year. So we're averaging here over a US population. And that contributes to a little more than half of our annual radiation dose per year in exposure. And if you look at the very top, you can see a tiny little sliver in pink. And this is occupational from nuclear power plants. This is less than 0.1% of the total radiation dose you receive in the year. So 0.1% is 1/1000th of this pie. Next slide, please. So let's see how this fits into context for some recognizable radiation sources. So starting at the bottom right, we can see a chest X-ray is 10 millirem or 0.1 millisieverts. So this is the equivalent of less than 2% of our pie. This is a single procedure. So if we have a single procedure of relatively high radiation, we would call this acute, right? We might be more willing to undertake nuclear medicine procedures, and there you can see many different radiation levels in this pictogram to utilize the benefit of radiation to help with diagnosis and treatment, and it can save our lives. If you can see on the left, you'll notice that people living in Denver, which is a high elevation, get more background cosmic radiation from the sun, so 80 millirem or 0.8 millisieverts, compared to people who are in College Station, like I am right now, which is about 30 millirem per year or 0.3 millisieverts. Again, these are chronic. These average over the entire year, and our bodies are used to this. They can repair. A person traveling, for example, and I haven't indicated this on our little graph here, but I thought it was an interesting tidbit, as someone who travels on a transcontinental flight above 33,000 feet receives about 3 to 5 millirem per trip, which is more than you'd receive if you spent 24 hours a day standing at the gate of a house of a nuclear power plant. So I made a couple addendums here. So let's take a couple of notes away here. So I've highlighted in the middle, you can see 6.2 millisieverts or 620 millirem is our pie, from our pie chart. So that's our average annual background for a US person. And I denote US person as opposed to a global person because there's actually a little bit less in terms of average medical exposures internationally compared to the US. At the top, you can see the annual dose limit for a nuclear power plant worker. So if you worked every year, this is your dose limit. It's very conservative, developed scientifically, and enforced by regulatory bodies. And you can see at the bottom, 1 millisievert or 100 millirem is the annual dose you'd get, that pink sliver from the pie, from a US member of the public from radiation exposure living near a power plant annually. Next slide, please. So I'd be a bad scientist if I didn't include some other type of graph here, except this is not a graph of radiation levels. This is actually a graph of how many times the word Fukushima was typed into global. And you can actually track these via Google Trends. So you can see here, no one really gave any credence to Fukushima until after the incident in 2011. So what I'd like for us to consider today is how is it that we parse good news from fake news being quite a popular term in the last few years. Credible sources are those that come from our government agencies and international agencies, such as the International Atomic Energy Agency. So even during Fukushima, Bill Nye got it wrong. Remember Bill Nye, the science guy. So you have information available to you. And I want you to, looking through some of these numbers, get an idea of what levels of radiation dose are. Right. I also want you to remember the number of 20 millisieverts, right? So remember our pi was 6.2, right? And I want you to remember this number of 20 millisieverts as we go to our next presentation. One other thing that the discussion of radiation dose that I haven't discussed today is associated risks, whether detrimental or not. I want you to remember this 20 millisievert number for low levels of radiation. This is a low level of radiation. We looked at it in terms of background, our pi. But because of low levels of radiation, so the equivalent of 2 total body scans, almost 2,000 people were evacuated from Fukushima, resulting in deaths just due to fears of low-level radiation. So the radiation deaths from Fukushima were the result of only 1 death, and that was from a radiation worker, a frontline worker. There were no excess thyroid cancer risks from screenings or other associated deaths. This is not another Chernobyl. And in fact, despite the tragedy from the earthquake and the tsunami being unequivocally tragic, perhaps what is a continuing tragic legacy is how nuclear contributed to the death toll from evacuations. And this fear has resulted in further stigma of displaced populations, which our next panelists will discuss. And just on my last slide here, if we can advance, I'd like to close off on this quote by Marie Curie, who was one of the pioneers in the discovery of radioactivity. And Marie Curie quite aptly said, "Nothing in life is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less." So if we'd heeded the wisdom of Marie Curie, there might have been a different outcome for some past events. Hindsight is 2020, but let's certainly keep this as a mantra going forward, as being open to learn. Thank you.
Thank you, Shaheen. And I have been told that my internet's a little unstable tonight, so I apologize if you're losing some of my words as I'm speaking, but hopefully you can hear me. Now let's hear from our next presenter, Dr. Ryo Morimoto. Ryo is a nuclear anthropologist at Princeton University. Through his ethnographic research, Ryo aims to create a space and a language to talk about radiation as an intrinsic component of our lives, rather than as something alien to us. After the accident at Fukushima Dai-ichi, he spent 6 years conducting research and listening to the experiences of people living along the coastline near the plant. He is currently finishing a book based on that fieldwork entitled The Nuclear Ghost: Atomic Livelihood in Fukushima's Gray Zone. We'll hear more about that concept of a nuclear ghost from him tonight. Welcome, Ryo, and thank you for being here.
Thank you, Véronique, and thank you so much for the Buesseler Oceanographic Institution for having this opportunity to talk about my research project. And I'm an anthropologist researching the post-fallout coastal Fukushima since 2013. And I lived there to find out, given what we know about the science of radiation, how people actually live, think, and act when there is a nuclear accident. One unique thing about the nuclear accident in Fukushima was that people all over the world saw the live footage of the hydrogen explosions in March 12 and 15 in 2011. As a result, the global community learned the name Fukushima searching the internet using the keyword like mutation. After all, isn't nuclear accident all about radiation exposure and its detrimental biological and environmental consequences? In Japan, people reacted similarly, problematizing the threat of radiation exposure the accident posed, especially to children. And culturally, radiation exposure triggered various past memories of horrible irradiation of human bodies from Hiroshima and Nagasaki in 1945. As an anthropologist researching why many people remain in the contaminated region, I started to learn a huge gap between outsiders' imaginations and insiders' experience of the nuclear accident in Fukushima. This image you're seeing captures the gap nicely. You can probably tell who the local is here. Today, I will share some of my research findings with you. But first, let me briefly explain my field site. Minamisoma is a city in the coastal part of Fukushima, about the size of Denver, Colorado. It's located 10 to 36 kilometers north of the Fukushima nuclear plant, and the only municipality within the 20 kilometer from the damaged plant that did not enforce total evacuation. As a result, after the accident, population dropped to less than 10,000, but in a year or so, the population back up to 45,000. In the very beginning of my fieldwork in 2013, when I was very suspicious and carrying around a Geiger counter to measure radiation in air, I met a woman in her early 60s at a Buddhist temple. As we're chatting, she casually mentioned that there's a nuclear ghost in Minamisoma. I was confused by this comment because all I knew was that in the Japanese conceptualization, ghost is a shapeshifter and appears because it has some message to the living. Taken by surprise, I asked her to speak more about how and why there is a nuclear ghost in Minamisoma. This is what she told me. Ghost is something some people see and believe in, but others don't see or believe at all. Once the ghost reveals to you, there's no turning back. It changes how you think about your past, present, and future. That's the nuclear ghost in Minamisoma. Not knowing what to say, I told her I was unsure if I believe in ghosts, nuclear or otherwise. She told me it was okay, but immediately pointed out that I carry a Geiger counter. So I must have been suspicious of imperceptible phenomena in Minamisoma. A Geiger counter is one way to ascertain the presence and absence of phenomena that you cannot sense. She had caught my inconsistency. Then she continued, "Are you going to use it to tell me that I should not be living here?" I left the temple that day very confused about what the nuclear ghost in Minamisoma was. Living in the city, I noticed that everywhere I went, radiation was visualized with monitoring posts, radiation maps, Geiger counters, decontamination, and gamma camera. In Minamisoma, unlike other places in the world, radiation was hyper-visualized. But on the contrary, residents avoided talking about radiation in public, nor people used Geiger counters to survey. Why? The way the residents experienced radiation most acutely was not with their bodies, but from the amount of money they received from the government based on where they lived within the city. If you lived outside the zone, you received $1,000 for 7 months after the accident. Inside the 30-kilometer zone, $1,000 for 18 months, and inside the 20-kilometer zone, $1,000 for 7 years and 4 months. So locally, radiation materialized as the tangible differences among the residents in the same city or in the region. As a result, many pre-existing social and domestic ties were damaged. People disagreed over how contaminated the city was. And at times, families were separated. Perhaps we can think of COVID and a disagreement over how serious it is or whether or not to wear a mask. What we know now is that evacuation and the politics surrounding radiation safety cause more damage than low-dose radiation in the city. However, the government and the electric company insist that radiation exposure is the only valid form of damage from the nuclear accident. In the context where radiation is highly expected and hyper-visualized, what is the nuclear ghost? Nuclear ghosts are residents and their experiences of the social effects of radiation, ignored by the government, experts, media, and the public, whose primary concerns are radiation's measurable adverse health effects. What the lady at the temple was trying to tell me was that when I was talking to her, I only expected to hear about the story of radiation my Geiger counter dictated, not seeing or believing her experience like she was a ghost. The moral of the story is this: understanding and talking about post-fallout Fukushima by foregrounding what is invisible over what is visible is what locals found dehumanizing and more damaging to their well-being than radiation. So what are some lessons from Minamisoma? I'll give you two here. First, a nuclear accident is not merely about the radioactive danger. Second, even if low-dose radiation does not cause immediate harm to individual bodies, when selectively visualized, it damages the pre-existing social and cultural fabric by causing divisions among people, the environment, and their interconnections. Thank you very much, and I look forward to Q&A.
Thank you, Rio. Really interesting. I have lots of questions myself after listening to you. So before we go on to our last speaker, we have a poll for all of you in the audience tonight. If you're joining us on Zoom, you should see a poll popping up on your screen with several options to choose from. And so the question is, how many naturally occurring radioactive isotopes are known to exist? And in case that term isn't familiar to you, an isotope is just a different form of the same element. For example, there's carbon-12, carbon-13, and carbon-14. Those are different isotopes of carbon. They're all carbon, but they have different numbers of neutrons, so they have different weights, masses. And only carbon-14 is radioactive of those. All right, so we've got our results here. So most of you went for the more than 3,000, and actually the number of naturally occurring isotopes is only 84. But those of you who said 3,000 weren't totally wrong. That's actually the number of naturally occurring and artificially produced radioactive isotopes combined. So many more artificially produced radioactive isotopes than there are those that occur in nature. All right, moving on to our third and final speaker for tonight. I am very happy to introduce Dr. Ken Buesseler. Ken is a marine radiochemist and director of the Center for Marine and Environmental Radioactivity at WHOI. Over the course of his more than 30-year career, he has studied the impact of on the ocean environment of atmospheric nuclear weapons testing, the Chernobyl nuclear accident in the former Soviet Union in 1986, and the meltdown at the Fukushima Dai-ichi nuclear power plant in 2011. Ken also uses naturally occurring radioactivity to study the ocean carbon cycle and its impact on climate. After Fukushima, Ken founded a community science campaign called Our Radioactive Ocean to track contamination across the Pacific Ocean, and we'll hear more about that from him in a bit. Ken, thanks for joining us.
Thank you, Véronique. My pleasure to be here. So what I want to do first, before I get into some science lessons, if we get to the first slide, is kind of tell you about my background a bit more. And you might recognize these. I grew up in the 60s, and these are already about 10 years old. These two movies, Godzilla on the left and Them on the right. And while I appreciated the drama at the time as a young kid, I didn't realize how connected they were, and they're connected to tonight's event, actually. So if we can go to the next slide, I'll talk about the first way they're connected. If you remember Godzilla, or if you haven't seen it, the very first version, there's a flash, a explosion of a hydrogen bomb took place in Bikini, and that caused the release of this monster from the deep. So a radioactive explosion, actually the specific test in 1954, Bravo, is the cause of the release of Godzilla from depths. Them is a US story. The first tests in Alamogordo, New Mexico, the Trinity tests, caused in that movie a mutation of these ants that came and grew to gargantuan sizes and terrorized Los Angeles. So nuclear testing was really what was behind a lot of this cheesy sci-fi. What was also interesting, I didn't appreciate, is that there were always science heroes who actually came up with ways to solve the problem. How do you get rid of these ants? What are we going to do about Godzilla? So science was there. Maybe in the back of my mind, I had an idea, even back then, that I wanted to study radioactivity in the ocean. So let's get right into that story then about radioactivity in our oceans. So the next slide is going to show you the relative scale for one radioactive form of cesium, cesium-137, and how much is in the ocean from different sources that we've already heard about. The biggest circle there in green is from the atmospheric nuclear weapons testing. Some 500 tests in the atmosphere released close to 1,000. The unit is a petabecquerel of cesium-137. You're going to hear a lot of crazy units. I'll be talking about becquerels at the K per second. That's a pretty small amount of radioactivity. Peta is a very big number. When you add it up, it's 1 with 15 zeros. So that's by far the largest source here on this slide of radioactive cesium. And most of it, the waterline there, fell in the ocean because we live in an ocean planet, 2/3 of which is covered by the ocean. Chernobyl came along in 1986, releasing about 10 times less, mostly on land in Europe. Fukushima Dai-ichi only 10 years ago. We're talking something 4 or 5 times smaller than Chernobyl, but because that reactor was on the ocean, I'll show some data shortly, but it was a very large ocean release of radioactive forms of cesium. And you see a small dot there from 3 Mile Island. That was actually quite a small source in particular of this isotope of cesium. But now the theme tonight is we live in a radioactive world. So the next thing I want to talk about on this slide is that there are other radioactive isotopes in the ocean. The 2 most abundant, potassium-40 and uranium-238, are many times more abundant than what humans have added. So where do these come from? Things like weathering of rocks. Rivers carry these in the ocean. They have really long residence time, so they build up over time. They have very long half-life, so they stay with us. And so they build up. And what my challenge is often is how do you measure that small amount of cesium in an ocean with other radioactive isotopes in it? And that's why I'm in a chemistry department. We have clever ways to separate these based upon chemical properties. So that's kind of a feeling for what's in the ocean, and particularly focused on cesium, but there are many other isotopes too, but that's kind of a clean example to talk about. Because we're going to move along now to Japan and talk about the levels of cesium in the ocean right after that accident and through today. And so to get all of this on one scale, we'll spend a little time on this graph. We're plotting in the vertical the relative amount of cesium, that same radioactive form of cesium in the ocean, with each circle representing a seawater sample collected. You see on the map on the right, the dark red is where the fallout was heaviest, near Fukushima Dai-ichi reactors. So this is right in the ocean near the reactors, the highest numbers observed. You'll also see a blue line on the bottom. That's down to 2 of the units in this graph. It's becquerels, that same radioactivity unit, per cubic meter of water, about 260 gallons. So we were everywhere in Falmouth. We always have 1 or 2 becquerels per cubic meter of cesium. But after this accident, the first couple of months, we had reports of 50 million becquerels per cubic meter, a very unprecedented level. And we wrote down here on the left, Black Sea after Chernobyl 1,000. That's the highest number we found going to that body of water after the accident in 1960. So truly unprecedented events. Now we're going to go over time now as we move along the x-axis from 2011 to 2020. So the next part of this graph, we're going to look at the next set of samples. So these were collected in the same location, as close as possible to the reactor, reported in those same units. You see they drop off, but then they kind of level to values above 1,000 for the next 5 years out to about 2015. Now, I changed colors here because I don't work for a government lab, but I do know something about the effects of radioactivity on marine life, and above about 1 million, you actually would have mortality, reproductive effects, things you could directly see in marine life. And so that's why those are color-coded here in red. You get below that level, it's harder to see those effects, but we as human consumers of seafood get very concerned about internalizing cesium. The effects are greater when we internalize radioactivity than if we're exposed externally. So that level I'm going to take down to 1,000 and see how it drops off and remains above that about 4 or 5 years. As a consequence, they shut down fisheries immediately and couldn't reopen them until they got below these levels. It could show in tens of thousands of fish that they were below levels that were considered harmful for human consumers. So let's go to the last part of this graph, and you'll see levels today out to 2020 on the right in blue. Again, every dot is an ocean sample at the same location, jump up and down, tides move in and out, and ocean currents change, and the sources do change. But basically, they're down maybe at 100 of these units if I looked at the latest data at that location, but still much higher than 2 that was there before. So we have to admit that the levels are higher today because of ongoing sources. Maybe we'll get to that in the panel. But they're blue because at these levels, we certainly don't have the same concerns. We're below a level where we're concerned about seafood safety. So those fisheries have reopened. And for things like swimming and surfing and boating, the exposure levels are quite low. And we're going to look at some of these numbers in the same units across on our coastline on the west coast of North America as we move ahead. But really, these are kind of esoteric units, right? A becquerel per cubic meter. What was the public thinking? What did this all mean? And so the next slide is one of those things we saw shortly after the earthquake and release of radioactivity. And this was used by those basically putting out disinformation with headlines, "The Pacific is dead." Pictures of the two-headed whale on the coastline of Mexico is another one I remember, or the starfish that were wasting on the California coast. Basically, this is a map of the tsunami height, not radioactivity. So if we can put out that, I want to be clear, this was used as part of a disinformation campaign to say the Pacific was dead, but that's not how the radiation looked. We're going to actually show you some models and numbers in the next couple of slides. But what this led to, if we can move on, is basically this fear in the public. Should it's safe? Can I go to the restaurants? Can I eat my sushi? Certainly, we could detect that radioactivity even in tuna that swam across the ocean. But as I'll show you, the levels had decreased even more as we got to our coastline. So let's go to those predictions. What would we expect from a release in Japan as that radioactivity moves its way across 5,000 miles from the coast of Japan to the coast of North America? So you'll see the colors start out red and yellow. So tens of thousands, 1,000 becquerel per cubic meter. I haven't changed the units on you. Same numbers we were talking about before. As cesium moves, it's a salt in the ocean, so it moves with the ocean currents. That plume stayed largely north of Hawaii there. The black dot's kind of in the middle right of your screen. But they're down to numbers about, again, 2, 5, 10. But this is just a model. I'm a seagoing oceanographer, so we wanted data. So let's actually look at the data to say how high these numbers are on our coastline. And so in the last couple slides here, this is a map, sort of like that first one, but now instead of time, it's just putting all the data together collected kind of on our coastline and between, say, Hawaii and Alaska, that vertical track there. And you see numbers, the light blue colors, 2 or less. That was that horizontal bar that was off Japan beforehand. So these numbers really are areas not affected. We could not detect in these years after Fukushima any additional radioactivity. So a great question, what was released, but it's always above a background. Any number higher than that, indeed, is higher because of the Fukushima source. The highest numbers there in kind of a dark brown color are about 8 becquerels per cubic meter. That number is still quite low. Remember, we're still about 100 closest to the reactors off Japan. 8, I don't want to be dismissive that there's zero risk. It's an additional risk, but you put that into dose equivalency and you swim in that ocean every day for a year. And that additional risk from human health perspective is about 1,000 times smaller than one dental x-ray that you choose to do. So these types of numbers would not stop me from swimming. In fact, they're lower than the values on the West Coast after those nuclear tests, right after those tests in the 60s. And then finally, I do want to thank the groups that helped me make this map. And that was done largely, almost exclusively through crowdfunding, crowdsourcing. Our radioactiveocean.org was set up early 2014 to respond to the concerns because we only had models. We had no federal US agencies monitoring radioactivity. So we enlisted people. Tell us where you want to sample. Go out and collect those. Santa Barbara on the left, the classroom of students went out as a student project. We sent out that red box. They collected 5 gallons of water. Families went out, Point Reyes in the middle photograph, the surfers in Santa Cruz. So they not only collected, but they fundraised so we could use high quality scientific methods to address their concerns and then put the data right up on a website and talk about what those different levels mean for human health and safety. So I don't want to be dismissive of anyone's concerns. Certainly those first couple of months off Japan, we had grave concerns, never had seen that before. But as that came to our coastline, they're much lower today. And so hopefully in panel, we can talk about some of those relative risks and think more about the oceans and maybe other radioactivity that's out there. I'll move on to the panel now. Thank you.
Thank you, Ken, and thank you again to Shaheen and to Rio. All right, it is time for questions from all of you. We've been getting quite a few. Just before I go to those audience questions, if Rio and Shaheen will join us again, I have a question kind of to kick things off for all of you. I was hoping you could sort of bring us up to date as far as what's the situation now in the region around Fukushima and at the power plant as far as contamination or environmental or health effects that we're seeing. Ken, maybe we'll start with you as far as sort of contamination.
Yeah, so as I was alluding to, in the ocean, we're in that blue zone. We're much, much better off than we were in those first couple of months. Now, we're still elevated, so we have sources. We have sources from the nuclear power plant, releases after rain and groundwater. We have rivers bringing radioactivity in from land. And we have along beaches, north and south, at least 100 kilometers or more span, many tens of miles where radioactivity is coming back out into the ocean at low levels. But I think as far as safety and fisheries, we're doing pretty well. I think we'll hopefully get some questions on tanks and what might happen next. But certainly, as we go back about every year, we've seen the levels vastly decrease over 10 years, but it took a long time.
We'll come back to that tank question in just a minute, but I want to go to Shaheen. I'm sort of wondering whether the residual contamination in the environment is at a level, even if it's a very low dose, whether over time, after a decade since the accident, or even over a lifetime for the people who live in the region, whether those might cause things like reproductive effects or health effects that are more chronic, like cancer or something like that later in life.
Great, thank you. That's a great question. Fukushima area is one of these areas where the population is being most heavily monitored for onsets of cancer and thyroid cancer, for example. And all of the studies to date have indicated that no one has received really any level of radiation dose, especially in the vein of thyroid monitoring, that could lead to, for example, a thyroid cancer. I think what the challenge is for recuperation in Fukushima is the combination of decommissioning the reactors there, which were damaged from an earthquake that was beyond a design basis of 1,000 years old type of incident. So they're working together, the international community with the Japanese community, to safely decommission those reactors and as well monitor the environment. But if you look at examples of Hiroshima and Nagasaki today, those are back to thriving cities. Given that there were nowhere near anywhere the level of detrimental health as a result of radiation exposure from Fukushima, I think that the population will eventually be safe and continue to return to that area to hopefully thrive once again.
And Rio, has anything changed? I don't know if you've been back recently to the area, but you were there for 6 years, so that's already a good stretch of time. Did public perception change or public understanding of radiation change over that time during which you were doing your interviews or since then?
Yeah, thank you very much. And I think, in terms of the local communities, once they make a decision to remain in the area despite the threat of radiation, I think they are kind of adapting to the understanding of the inevitability of the radiation in the environment. But this is not to say that people who decided to say evacuate and never come back will still hold this idea of radiation being very dangerous to them, right? So I think one of the things that, continuing on to my presentation, that I observe is that there is a huge divide in terms of how people understand. You will see the divide between the anti-nuclear or the pro-nuclear, and then there's not that much between. But what I would like to say is that the one huge difference is the size of the evacuation zones being reduced from the little bit over 1,100 square kilometer to 370 square kilometers now. So as you can see that the contaminated area is being reduced right now. So that gives a very different sense of the landscape in the area.
Yeah, we've had several people actually asking about the timeline for rehabilitating the re-evacuated areas. Has the government put out a sort of timeline about that, or?
There is no definite timeline. Right now, what's happening in those areas is that the government and the local communities having actually discussion first time in 10 years to really think about was the 20 millisievert limit appropriate? Given what Shaheen earlier mentioned about how evacuation impacting the health of residents more than the radiation exposure. So it took us 10 years to really talk about what it means to be in the area.
Yeah, just to go to that point. So how many people actually died from radiation exposure at Fukushima?
I believe it was only one who died from acute radiation syndrome.
I think you're correct. And the other 2,000 or so who are connected to the accident that died were really deaths due to evacuation, meaning they were made to travel when really they weren't physically able to travel, and they didn't survive that move, essentially, right?
That's correct.
So we've got a lot of questions here. Let's see. Let me give this one to Ken. How did you yourself go to Fukushima, and did you collect data yourself personally there?
Yes, I'm on the ocean side, so I can be a kilometer, less than half a mile offshore. We have free access both on the ships we brought there in 2011. The Moore Foundation sponsored our first international trip there. But since then, about once a year, we've been going back with Japanese collaborators to collect samples. I think that gives a lot of confidence to what they collect. So the dots I showed, the colored, that was collected by Japanese, that's Japanese data. I think they've done a pretty good job collecting, maybe not as good a job explaining what this means. And so people hear these numbers, they don't understand, what are my risks? Where else should I be concerned? But and it goes beyond. I think we had said just before this about casualties and deaths. I mean, this is a lot bigger story, right? Whole fishing fleets were destroyed by tsunami. They can't build back a productive fishing industry if people won't buy the seafood. So there's a lot of social, economic cost to this, and tens of thousands of people can't move back. So the consequences, I think, will be here for decades to come.
Yeah, that question was from Jessica, by the way. So let's see here. This is sort of an interesting side question. I don't know if you'll be able to answer it, Shaheen, but since you mentioned radon in basements in Pennsylvania, and we actually have that here on Cape Cod as well, Susan is asking whether there might be radiation in fracking water. Also a big activity in Pennsylvania.
I think that's an apt analog, given that, you know, fracking comes from underground types of mining activities. I'm not specifically versed on the radiation doses associated with fracking, but they do come from similar sources from the earth. I'd be happy to get back with the questioner and provide some further information.
And kind of a related question from Sarah about the average risk of developing a health condition from radon exposure. I know the risk if you have radon in your basement and you're exposed, say over, you know, a lifetime of living in the home, is that you could develop lung cancer, for example. But what's sort of can you give an average risk? I don't know that you can, since radon in the soil varies so much from place to place, but.
Yeah, it really does vary. And like I said, I'd be happy to answer any questions related to radon offline.
Okay, perfect. So let's go actually to talking about the wastewater at the Fukushima plant and other things going on with their decommissioning. But I know there's water being stored in tanks on the site. Ken, maybe you can talk a little bit about that.
Right, there's really two parts to the story. So what's going on since 2011, after the earthquake? Those buildings were damaged, groundwater is leaking into them. And so this combination of water coming into the buildings every day and keeping the reactors cool, even when they've melted down, there's cooling water that has to flow through the system, but it builds up every day, hundreds of tons, and now over 1,000 tanks, 1.2 million tons of water stored on site. So the canonical image is all of these blue and gray tanks. Now, they have been cleaned up as best as the technology allows for many forms of radioactivity. That doesn't allow for the cleanup of tritium, a radioactive form of hydrogen. And so that's been what's been talked about as these tanks accumulate, the water accumulates. But, you know, we knew as scientists there's probably more in those tanks than just that form of radioactivity. And again, as part of the communication, I think not really misinformation, but the lack of communication, because it took 7.5 years for them to admit that there were other more harmful radionuclides still in those tanks that were not 100% removed. And so 70% of the tanks would need additional remediation to have levels of tritium where only tritium might be the concern, because the plan so far is released to the ocean. And for tritium, that might be a low risk, but if you're talking strontium-90, ruthenium-106, other cobalt-60, these things, one, are far more dangerous in terms of their radioactive dose. As an oceanographer, I know they accumulate more likely on the seafloor, so they're not going to dilute like that model I showed you of cesium. They're going to accumulate nearby, near shore, and therefore they're also going to get in seafood to much higher levels. So any plan moving forward has to be more transparent about what's in the tanks and show us the data, remediate those tanks, and then show us and make plans, and stop talking only about tritium and consider other options. I just think, you know, there's many levels to this story, and that's more of what I worry about, these additional sources and how they could definitely impact the area today. And if not for health reasons, for just the fishermen who are now being told that as they've recovered their fisheries, now they're going to tell the public we're purposely releasing radioactivity in those territorial waters. Go ahead and buy our fish. That's just not going to go over very well.
Absolutely. Rio, did you want to add anything to that?
No, I think that's pretty good. I think the only thing I would like to add is that we also need to consider like something other than science. Because one of the issues after the accident being that the government and the electric company decided to stay objective, meaning that only talk scientifically about radiations or radioactivities, which caused a lot of issue in the sense first, like the residents who are not educated in that level, they're bombarded with all this data that, as Ken was saying, without any interpretation. Another thing was that, this feeling of uncertainty is different from engineers and others saying that it's safe, right? So I think one important lesson from Fukushima being that, as a scientist, we ought to be able to not only provide the data, but also to be able to, have these sort of credibilities so that the people can trust your expertise.
Yeah, actually, that's a question I wanted to bring up about, because a lot of what you've said has been about sort of communication or miscommunication, and how big of a role that played in making the aftermath of the nuclear accident much worse than maybe it needed to be. And how can we do a better job of communicating about health and environmental risks when people do have very widely varying experiences of them and understandings? And actually, that's kind of a question for all of you, since it's something you probably all think about to some extent in your roles.
I can start. I think that communication, especially of these magnitudes of types of events where there are complex scientific models being interpreted that have very tangible impacts on people's lives, not just being a number on one side of a boundary or another. This is a continual challenge. And I think the key is to start as early as even in schools. I'm part of some outreach events as part of the American Nuclear Society to get students and young people engaged on what does nuclear mean. Since there's radiation around us, natural, medical, what does that mean in terms of those quantifiable numbers? And what does that translate into in terms of a daily risk? And I think that helping people understand on that basis is one of the key success strategies. I think also having, and we've seen this as well as a lesson learned from COVID, having concerted talking points, strategies, and a key communication strategy that is cohesive and consistent will keep from having misinformation and associated uncertainties, creating a public that is less than confident in those who are delivering the information.
Ria, what do you think in your experience talking to local people? What could have been done differently or to make things better for them?
I mean, that's a very difficult question. I guess, resident might say, well, if we didn't have the nuclear energy, that would have been the best option. But one of the interesting thing was, the group of people I worked with in Minamisoma, despite the fact that their city is relatively close to the nuclear power plant, many of them in their everyday life didn't even think about the power plant was being nearby. And one of the things that I discovered doing archival research and why not was that was partly because the fault of the government and electric company basically only saying that nuclear power is safe, right? There's nothing about it. It's risky in order to make it possible for that structure to come into being. The result of which what I observed in the area was that people just learn not to even think about it or to try to learn about that stuff, right? And then this was such a huge difference from in the 50s, in the beginning of the nuclear power plant construction in Japan, when newspaper was busy propagating by giving citizens the knowledge of radiation exposures and then danger, right? Especially, and there the company had to convince people who only remember Hiroshima and Nagasaki, right, to be okay with the idea of having nuclear anything. So I think one of the important lessons, at least to me, is that, first of all, we really need to think about different ways other than science to be able to talk about the radiation in our life, like this event. And then, I recently tried to write a letter to the local community member to tried doing some of that work, but it's very difficult. But I think also another thing is to have interdisciplinary conversations, scientists and social scientists and the humanists to really talk about on this issue.
All right, Ken, you're getting the last word.
Well, my perspective is I've talked to both, pro-nuclear and anti-nuclear groups, and I kind of get upset with both sides because I often see in the governments, the pro-nuclear side, this dismissive attitude. Oh, just trust us. We'll tell you the truth. And in fact, there's a legacy of not giving out all the information. Maybe not lying, but not telling us until after something has happened or they knew more than they were telling us. And I think that doesn't work. Obviously, that leads to this lack of transparency and mistrust. That's been there throughout, I think, the nuclear era and nuclear power. The other side of response to that are people saying, stay out of the ocean. Every fish that washes up on the West Coast is dying because of Japan radiation. That's simply not true. So what I try and do is basically say, you can be for or against nuclear power. Just don't scare people from swimming on Malibu Beach, California. That's a different question. We can address that by looking at the levels, compare them to relative amount off of Japan. And I'd like to say, that amount of radiation in California, the difference between that and 2011 off Japan, it's like the temperature on Earth and in the core of the sun. It's 50 million times higher. And that will have a very different health effect. So you give them enough information to know when they're in harm's way and to weigh these relative risks against other things in their life. That's their choice, not mine. And I don't try to tell them if it's safe or not, but just try and point out these differences. And hopefully from that experience, they can make their own choices, decide what where they want to go swimming, what fish they want to eat, and if they support certain forms of energy or not.
I want to get in this question from Leslie. She says, how can we represent the complexity of the lived experience on the Fukushima coast without inadvertently downplaying very real concerns about long-term health risks? I don't know if that's a question for Rio, maybe.
I'd like to hear Rio's take on that.
Yeah, no, I actually noticed that question. It's actually a wonderful question. That's something I struggle a lot with. What I've been trying to do is to talk about, what's actually been happening that we haven't paid attention to. And then this is not to say that the effect of radiation, it wasn't significant. The reason why I talk about the importance of the social effects of radiation is that if we really want to stay with these communities and pay attention to how they will be doing 10 and 15 years from now, we ought to be able to understand what is it that they are struggling right now. So I think my answer to the question is that my position is not to downplay the potential impact of radiation exposure, because it's not like there's been an experiment done, and putting people in a low dose radiation environment for a long time, right? You can't do that kind of experiment. So science is not knowing everything. But if we really want to understand the potential physical effect from the low dose radiation, we really need to stay with these local communities and listen to what they're saying that they struggle right now. And then one that I've been focusing on is the social effects that they've been experiencing that haven't been addressed, because much of our question being, are they irradiated? If so, how much? Are they getting cancer right now, right? So I think that is the way to answer that question, but that's a very important question, something I struggle myself.
All right, I'd like to do one quick question here from because I know I'll get in trouble if I don't ask. This is a question actually from the son of a colleague who's going to go for his PhD in nuclear engineering soon, and he wants to know, Ken, how many samples did you actually get from the public as part of our radioactive ocean project?
Several hundreds. I stopped counting. I mean, that map was completely blank. So you can count the dots as well as I can. Some were ships of opportunity. So it's public funding of a pre-planned voyage where people collected for us, 500 plus people. I was pleased with the range of groups participating, from someone in Malibu Beach saying, look, I just want a number. Here's my money. Tell my neighbor that it's okay to go surfing or not. And others who really painstakingly set up small fundraisers with tens, scores of people trying to get enough so they could know what that amount might be and track it. So interest has gone down, which I think is good, because that means we've kind of seen the peak of radioactivity. In fact, the levels are going down, but they're still measurable. And I do like to say it's as important to measure these numbers when there's no concern, right? You want to know what was there before something happens. So if we are to operate reactors safely around the world, I know I'm going on a long bit here, but then we need a cadre of scientists who can actually go out there, make these measurements independently from the operators, and say something about this, not just cesium, but other radioisotopes in the ocean. And unfortunately, we kind of fall between the cracks in the US system for that. But by bringing in the public, I think I learned that they're eager to know more, and they actually learn something by participating. So there's definitely a benefit from bringing the public in this.
Absolutely. So one quick go round for each of you, a closing question. Overall, in your opinion, is radiation a good thing or a bad thing? Do you see it more as a tool that we can control to our benefit, or as a phenomenon whose health and environmental risks outweigh the benefits? Ken, since you were talking, why don't you keep talking, and then we'll go to Rio and we'll end with Shaheen.
I actually don't like the question in the way of good and bad. It's part of our world. Right. There's many uses, medical uses, energy if you want, weapons, which we can argue about. I use radioactivity as an ocean tool. How old is that water at a certain place? How quickly does it get it there? We take advantage of these disasters like Chernobyl and Fukushima to study those ocean currents. So there is something positive there, but obviously when things go wrong, they can go horrifically wrong for large numbers of people, right, on land in these accident sites. I went back to the Marshall Islands recently, and 4 generations later, they're still asking the same question: is it safe? And so for those groups of affected people, I think the answer would be no. This has really been bad for them, for their society on those islands that they can't return to. So.
Rio?
Yeah, I mean, like Ken, I don't like the either or kind of question. I mean, again, because it's everywhere. I think my thing is that, if I say like radiation is not good, it's in the sense that, those things are distributed unevenly across space and communities, and then so say that we can stay healthy and then get the good side of radiation because we don't have to deal with a structure like nuclear power plant, which comes with some risk that the designers knows, hence they cite those things away from us. Right. So I think, in that sense, as the social technology that produces or reproduces this, exposable community, I would say radiation is not good. And then there are many ways that we have to think carefully to improve our relationship to radiation, which is everywhere.
Yep. Shaheen?
All right. I also have to agree with the other two panelists. It's an either or question. And I think that I can understand the concerns regarding radiation, its historical legacy and detriment in certain communities. But I also would like to encourage this community, now that we're in a time where you can conduct your own investigations, reach out to government, professional societies, nuclear industry, and ask questions that you have. Don't wait for something to trigger, right? And I'd have to say that given the operation of nuclear since being used for peaceful purposes, nuclear has offered an extremely safety record. So I encourage you to explore that yourself. And I think in terms of nuclear going forward, we're discussing new technologies, robust technologies, small modular reactors as a solution for climate change, new modalities in using nuclear technology, including isotopes produced from these reactors for cancer treatment and diagnosis. I think it's a very complex question that each of us needs to be able to ask and answer questions for ourselves to evaluate how is it that nuclear may be beneficial or detrimental in each of our individual lives.
All right, I think we're going to leave it there. That's all the questions we have time for, unfortunately. Before we close, I want to say a big thank you to Shaheen, Dewji, Rio Morimoto, and Ken Buesseler for participating in tonight's event and for sharing all your views and insights on this complicated topic. Thank you very much.
Thank you.
Thank you.
And thank you also to all my WHOI colleagues who have been working very hard behind the scenes to make this event possible. And to all of you out there who joined us, thank you. Tonight's event was the third in our third season of WHOI's Ocean Encounters virtual events. Our next Ocean Encounter will be on Wednesday, April 28th. So mark your calendars, Wednesday, April 28th at 7:30 p.m. The topic, as you can see there, will be the deep diving human occupied submersible Alvin. We hope you'll join us for that. To register or to find out more information about our Ocean Encounters events, please visit whoi.edu/ocean-encounters. You might also want to take a look while you're there at the very cool merchandise in our online store. That's shop.whoi.edu. You'll get a 15% event discount for joining us tonight. Just type in the discount code OCEAN. If you enjoyed tonight's Ocean Encounters program, you can be part of WHOI's solution-based approach to ocean science. Please consider becoming a WHOI member. You'll be providing crucial support for our science, engineering, and educational programs, and you'll get some great benefits in return. Membership starts at just $35 a year. The average gift is $100, but any amount helps. Your support will make a difference. On behalf of Woods Hole Oceanographic Institution, thank you and good night.
Out where the seas are the deepest and the mysteries the greatest lies our future. The ocean is our last unexplored, ungoverned frontier, the life support system for our planet, inextricably linked to our climate and weather and to the lives and livelihoods of countless people around the globe. But even against the ocean's vastness, humankind can be a formidable force. What happens next demands action that is rooted in scientific understanding and unvarnished truth, because our world stands at a fork in the road. In one direction, we watch the ocean being catastrophically altered beyond its ability to sustain us. In the other, understanding outraces exploitation, and we help steward and protect this most precious shared resource. What will be the legacy of the 21st century? Here and now, the world's most impressive collection of minds passionately dedicated to ocean science, engineering, education, and policy has a role to play. With the expertise to know what works and a trusted voice to present the facts as we uncover them, we can shape the future. We can inform governments, businesses, and conservationists. We can be the catalyst for change and unleash new knowledge in service of society. It is more than our responsibility. It is the defining moment of our generation. We are Woods Hole Oceanographic Institution, and this is our time.